Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everyone. It's my great pleasure to welcome back Dev Malia, who is a professor at Duke University. Dev Malia has had a long association with Microsoft Research, being an intern here multiple times and a postdoc, and now a visitor. And he's going to tell us about energy efficient scheduling in the non-clairvoyant model. And most of the work was done actually when all the authors were here. When Dev Malia was a postdoc, Yossi was a visitor, and Z was an intern, and this won the best paper award at SPAA. So overall, it's been a very productive effort from all of us. So over to Dev Malia.
Thanks, Nikhil. So as Nikhil mentioned, this is joint work with Yossi Azar and two authors who are in the room, Zhiyi Huang and Nikhil Devanur. All right, so this talk will be about going green. And what we mean by that is we would like to compute in an energy efficient manner. Now, there has been growing interest in energy efficiency in computing, both in the theory community, where energy is now increasingly being treated as a first class resource in addition to traditional resources like space and time, and also in practice, because there are several applications such as those in data centers where it's important that algorithms are aware of the energy usage of a particular scheduling plan or a particular execution. In fact, scheduling jobs on data center on machines is one of the key problem domains where energy efficiency plays an important role, which is exactly what we will be talking about today. And there are two paradigms of energy efficient scheduling that have been popular, and these two paradigms come from the two dominant application domains where energy is an important resource, and they represent sort of the two extremes of computing as we know. So one domain is our data centers, which is sort of the highest or the largest scale computing that we see today, and there the dominant technique for managing energy is what are known as power down schedules. So what that means is that at certain points of time you shut down some subset of machines in the data center, allow them to cool, and restart them after a while. And there has been some growing body of literature which talks about algorithms for power down scheduling. But what we are going to talk about today is at the other end of the spectrum, on handheld devices, where again energy is an important resource, and there the technique for managing energy is somewhat different because you can't quite power down devices. So instead what are used are known as speed scaling processors. So what does this mean? It basically means a processor that can run at various energy levels. So either you can run it fast and then it processes jobs faster, but it consumes higher levels of energy, or you can run it slower and then it consumes less energy, but it will take a longer time to complete the same job. Okay, so this is what we'll talk about today. In particular, we are going to look at what is one of the most basic problems in this domain. So you have a time axis and jobs arrive over time. Okay, this is standard scheduling. Now what are the jobs characterized by? So jobs have a release time. At some point of time you get to know that the job arrives in the system and you know that the job needs to be scheduled. So that's the release time of the job. Jobs have an important score which we call density, and we'll see why it's called density soon. It also has a volume. This is the total amount of computation that the job requires, and we will define the weight of a job to be the product of the density and the volume, okay, the product of the importance and the total amount of processing that you need to do. So these are the parameters that define a job for me. Now all these jobs come online or come over time, and they need to be scheduled on a single machine. So I just have one machine, I have a bunch of jobs arriving, the jobs need to be scheduled on the machine. The key feature is that this machine is speed scalable. So I can run this machine at various different speeds, and depending on how fast I am running the machine, I will consume a certain amount of energy and I will complete the jobs at a particular time. Okay. So what is the problem then? The problem is to decide two things. First, if I have a bunch of jobs that are awaiting processing, I need to decide which of them I should process on the machine. The machine can process only one job at a time. Okay. So that's the first selection. That's the first selection that I need to do. And then once I have selected the job to be processed on the machine, I need to specify the speed at which I'll run the machine. So remember, the machine is speed scalable, so it can run at various different speeds, and I need to tell you what speed the machine is running at any given time. Okay. So these are the two things that the scheduler should tell me. And the way the speed shows up is that it impacts both the energy and the processing time. In particular, the rate of decrease of the volume of the job that's remaining, that's being currently processed, and the volume that remains decreases at a rate that's equal to the current speed. Okay, so if I'm running the machine at, let's say, speed 10, that means that for every unit of time, the remaining volume decreases by 10 units. Okay, so that's the natural definition for speed. And how does speed influence energy? Well, the influence is through what's usually called a power curve. Okay, so this is just a mapping from speeds to energies, or speeds to instantaneous powers. Okay. And typically we will assume that this power curve is a convex curve. It's a small polynomial function of the speed. So about s cube or s squared, somewhere in between. Okay, is the setup clear? Okay, so this is the setup. Now the question is, what am I trying to optimize? So at a high level, it's clear what I want to optimize. I want to optimize two things. First, jobs shouldn't wait in the system forever. So I want to optimize delay or latency. And second, I should not be running my machines at crazy speeds. So I also want to optimize energy. So at a high level, these are the two things I want to optimize. Energy is quite easy to quantify. So it's just the area under the power curve. So at every instant of time, you're running your machine at a particular speed. That translates into a particular power consumption according to the power curve, and energy is simply the area under this curve. But how about the delay? Okay, how do we quantify delay? The standard way to quantify delay is by using what's known as flow times. So what's flow time? It's basically just delay but multiplied by weight. So you take the difference between the completion time and the release time of a job. This is the total time that the job spends in the system, and you multiply it by the weight of the job. Okay, and that's the flow time of the job. You sum it up over all jobs. That's your quantification of delay. Now, for the purpose of this talk, though it's not strictly required for the result, but for this talk, it will be convenient to introduce a slightly different notion of flow time. It will make our life a little easier. It will make things geometric. We call it the fractional flow time of a job. And here's a way to understand what this means. Take every job. Think of it being split up into very small jobs, let's say epsilon volume. Okay, there are zillions of such jobs. Now for each of them, you compute the flow time according to the formula that you had earlier. Okay, so each of these small pieces of the job get completed at a certain point of time. You subtract the release time of the job from it. All of these jobs are released at the same time when the entire job shows up. You take the difference and you sum it up over all these small pieces. Okay. So that's the fractional flow time of a job. And in this talk, I'll restrict myself to fractional flow times rather than going to integral flow times. Okay, all the results do generalize. So one way to think of the fractional flow time, as I said, is that it's the sum of flow times of these infinitely many parts. But an alternative view is that in fact, it's the integral over the total weight of all jobs left in the system at any point of time. So if you think about it, at any point of time, which are the jobs contributing to your flow time? Which are these infinitesimally small jobs contributing to your fractional flow time? It's exactly those jobs that are still in the system that haven't been processed. Right? So this is simply the integral over all the remaining weight over the entire time axis. Okay? So therefore, it can in fact be drawn as, so if I draw the curve of the remaining weight instantaneously, and take the area under this curve, that's in fact the fractional flow time of the job. So these are the two things that I want to optimize, and as is standard in the literature, what I'll actually do is, oh, by the way, so sometimes the fractional flow time might also increase because new jobs are released and therefore the remaining weight increases. And what I'll do as following standard convention is that in fact I'll optimize the sum of these two quantities. Okay. So summing these two, by the way, you can, all the results hold even if you scale these in whatever way you want. Okay, so you can change the scale on the two, you can take any linear combination.
So can you also say that I give you a bound for the...
No, that's stronger, that's not
like by
clear,
criteria?
that's not clear,
Even the...
that's not clear. Yeah, that's not clear. You will see where, so it's almost, so the part that we are doing is going to give you by criteria like bounds, but then we will piggyback on something that was previously known, and there the bounds are not quite by criteria.
So there you have the additional task of figuring out the branch. Don't know. Good.
So you will convert apples to oranges.
Yeah.
If you won't, then it naturally.
Yeah.
So are the jobs preempted?
Yes. Okay, so preemption is free and allowed. Okay, so that's the problem. Again, any questions about the problem? Okay. Okay, so what was known for this problem? Well, what was known was in what's known as the clairvoyant setting. So in this setting, when a job arrives, all the parameters of the job are revealed. Okay. So when you see the job, you get to know its density, its weight, its volume, all the parameters. And for this setting, there was a series of works which I won't quite go through, but the key one that we will really use is the following observation. It says that if I have a bunch of jobs arriving over time, the right thing to do is to use the following two rules. So remember, why do I need two rules? Because there are two decisions I'm making. Which job should I process and at what speed? So the job to process is given by this HDF rule, which means highest density first. So among all the jobs that are awaiting processing, I look at the job which has the maximum density, that's the job I should process. Okay, this is sort of intuitive, right, because that's the one which will differentially add the most to my weight. So that's the job I process, and at what speed should I process it? Well, for that, the first rule says that you should set the power, the instantaneous power, to be exactly equal to the total remaining weight of all jobs in the system. Okay, so that's the P equals RW rule, and we'll see why this gives certain.
The units don't match, no? What do you mean power being the remaining weight?
So take the entire remaining weight.
Yeah.
Because
Of all
when
jobs.
the units goes out, minimizing the sum, right?
So the units are already matched in the sum. Yeah. Okay. And what Bansal-Chan and Prus showed was that these two rules in conjunction give you a two competitive algorithm. Okay, so the total value of the objective produced by the algorithm is at most twice that of an optimal solution. But they don't give any, the competitive ratio is not in terms of each individual objective. If it were, then what Mohit was suggesting, some kind of bi-criteria approximation would have been possible.
What is epsilon?
Epsilon is, oh, where is epsilon showing up? I think it shows up in, let me think. Nikhil, do you remember where epsilon shows up?
I think it's super epsilon or any epsilon. Maybe it's.
Yeah, I don't remember.
I think they're considering arbitrary power function, and they need to kind of make it convex, and then do a kind of approximation of it, so that it's like maybe strictly convex or something.
Oh, it's like the number of oracle calls.
So it's a technicality.
Yeah, it's a technicality. It's maybe the number of oracle calls into the power function, something like this. Yeah. Okay, so that's the rule that was known. Okay. So how does this algorithm work? So if you think of drawing the the power curve over time. So let's say I have only one job at the beginning. So I set my power to be equal to the weight of the job. Okay, that's the total remaining weight. And then this job keeps getting processed. At some point, a new job is released at time R2. Now immediately I bump up the speed of the machine, right? Because I want to keep this, I want to maintain this rule that the remaining weight is equal to power, instantaneous power. And also, if the second job that was released is a higher density job, I in fact preempt the first job. I take the red job out of the system, I put the blue job in. Okay, as you can see, the blue job has, well, maybe you can't quite see it, but the blue job has a steeper slope, which just indicates that it is a higher density job. That's why the weight is decreasing faster. And then once the blue job finishes, I resume the first job. Okay, so this is the kind of power curve that the clairvoyant algorithm gives us. The question is, what do we do if we don't know the remaining weights? Okay, so we don't know the weight of the job, which means that we can't quite run this algorithm because even at time 0, I need to know the total weight. Okay. So before I go on, let me mention that so there are two different models in which you can think of non-clairvoyance. You can either think of knowing the total weight of the job when it arrives, or the the density of the job when it arrives. Of course, if you know both, then you know all the parameters. Okay, and the one that we will consider is the one where we know the density, so we know the importance of the job, but we don't know the total weight of the job. Okay, and therefore we don't know the volume either. Now there has been a little bit of work in the other setting, where you know the weights, but you don't know the densities when they arrive, and there are some results, but these we won't concern ourselves with this. Okay, so this is the algorithm in the clairvoyant setting. Now one thing to note here is that the area under the curve represents both the parameters that we are trying to optimize. So if you remember what I drew these two curves. One was the instantaneous power curve, and the other was the remaining weight curve, and I said that the two objectives are in fact the areas under the two curves. Now here the two curves, the algorithm has been chosen in a way such that these two curves are exactly the same, right? Because power equals remaining weight, and therefore the two objectives are in fact the same area under this curve. So what these guys really showed is that the area under such a curve is at most the optimal value, whatever is the optimal objective. Okay, and therefore they got their two approximations. Now there's one property of this curve that we will use a lot, and let me just state this property at this point. It won't be clear why this property is important, but we'll slowly see how it can be used. And the property of this curve is that if you simply take one of these curves, okay, so if you just take the red curve for instance, what does the curve depend on? It only depends on the density, right? If I tell you the density, then you can draw the red curve. Or if I tell you the density for the blue curve, you can draw the blue curve. So if I draw such a curve and look at the two areas, the area under the curve and area above the curve, then just simple math shows that the ratio of these two areas is between 2 and 3, and crucially is independent of the weight or the densities. So this curve of course depends on the density. If the density is higher, then the curve is steeper, right, because the remaining weight drops faster. But irrespective of what the density is, and therefore irrespective of what the actual slope of the curve is, the ratio of these two areas turn out to be identical, and it's about 2 or 3. And in fact what this means is that this also holds differentially, which means that if I start the curve not from 0 but from some other point and draw a little bit of the curve, then again if I take the two sort of horizontal and vertical segments and compare these areas, so that ratio is also exactly 2 plus 1 over alpha minus 1. Okay, and we will call it the differential universality property. This is a property that we will need in the rest of the talk. So at this point this is just a property of a particular differential function. Okay, good. So let's go back to the uniform density case. So ultimately we will look at arbitrary densities, jobs having various different densities, but let's start off by just looking at a situation where every job has the same density. Okay. So this is how the clairvoyant algorithm looks. Now what do we do for the non-clairvoyant algorithm? So let me simplify even further. Let me say that there is just one job in the system, there is nothing else. At time 0 I get one job and then I do not get anything more. So this is what the clairvoyant algorithm does, it is just this curve. Now it is not clear what I should be doing in the non-clairvoyant case, because note that I do not really know W1 at time 0. So I can't quite simulate this curve in the non-clairvoyant scenario. Instead what we do is we flip the curve around. So what I can do is I can simulate this curve in reverse by simply setting my power to be the processed weight rather than the remaining weight. Okay, this is just a mirror image of the curve on the left. But why is this any good? So what was happening in the clairvoyant case? The flow time and the energy were both equal to the area under the curve. For us, well, we have flipped the curve around. So the energy still remains the area under the power curve. Energy by definition is the area under the power curve, and therefore the energy consumption is the same in the two algorithms. The problem is with the flow time. But then if I look at any time instant, the processed weight is the height of the curve. So the remaining weight is the remaining, it's the part above the curve. And therefore the if I integrate over time, then the flow time in fact is the entire area above the curve rather than under the curve. But then our universality property says that these two areas are not very different. Right? That's exactly what the universality property was saying. So if I simply use the property as is, I'll get a comparative ratio of about 2. Okay, for the single job case, for the very simple single job scenario. Any questions about this one? Single density. Sorry, well, this is not even single density, it's just single job. No job is being released in the interim. Okay. So let's make the next baby step. Let's have 2 jobs. Again, uniform density. The second job is released at time R2. Now life is not so easy. Ideally what we would like to do is to again flip these curves around and run an algorithm which basically flips the power curves around. But can we do this? Well, not quite, because we don't know where to break on the right. Right? So in particular, we don't know the remaining weight of the first job when the second job was released. To know this, I have to process the entire first job. Otherwise, I don't know the weight of the first job. And therefore, I don't know where I should break that curve and start again. Okay? So this doesn't quite work. So instead of that, let me try to play around with these segments on the curve. So what I do is I take out the blue segment. Firstly, I think of this clairvoyant algorithm as a last in, first out algorithm. So note that all the densities are equal, so it doesn't really matter which job you are processing. However, for the sake of for easier explanation, let me just think of this as a last in, first out algorithm, which means that the blue job, once it arrives at R2, preempts the red job, and that is the one which is being processed, and then the red job resumes. Now let me take the blue job and move its curve to the end. Okay? So there's no semantics here. I'm just taking a part of the curve and moving it somewhere. Okay? So this is the curve on the left. And we'll try to simulate this curve in reverse rather than the original curve. Okay? So what do? I keep running the first job till it completes. And at this point, I want to start my blue job at this height W1 prime. But what is W1 prime? It only depends on the value of W1. That's the remaining weight when the second job was released in the clairvoyant algorithm. It does not depend on the actual weight of the second job, it just depends on the weight of the first job. So that's something I in fact do know in the non-clairvoyant setting, since I've completely processed my first job, the red job. Okay? So therefore, I can simulate the blue curve in reverse at the end of processing the first job. But why is this any good? Okay, so I have flipped it around, but I have changed things, changed the order, and maybe that's messing up with my proof. To see why it's good, let's do a simple analysis. So what are the remaining weights at any point of time in the algorithm, in the non-clairvoyant algorithm? Well, till time R2, the remaining weight is just given by W1 minus the processed weight. At R2, the second job is released, so the remaining weight goes up by W2, and that's how it remains till the end of the first job. Okay, is that clear? Okay. So now let me split up the clairvoyant areas into A and B. This is sort of the natural split. And the non-clairvoyant areas into A prime, which is for the first job. So remember, for non-clairvoyant, you have to account for area under the curve as well as above the curve. So that's A prime. And then B prime are the remaining weights due to the second job and the energy due to the second job. So those two, the vertical and the horizontal segments, are B prime. So A prime I can charge to A by just using my universality property. That was what I was doing for a single job. Okay, so charging A prime to A is just the same as the single job. I simply do that. So A prime and A are gone. I somehow need to be able to charge B primes, the two segments that I have drawn as B prime, to B. So let me move the B prime up and join it with the other segment, and move the B back to its original location. Okay? So now note that what is B prime? What's the horizontal segment in B prime? It's in fact this segment, the segment that I called B, extended to the end of the algorithm. These two lengths are exactly equal. It's the total time minus R2, the release time of the second job. And now what should I be using? Well, I'll just use my differential universality property now. So I want to charge the two segments, the horizontal and the vertical segment, to the area under the curve, which is exactly what the differential property was doing for me. So I simply use my differential universality property and charge B prime to B. Okay, and therefore I can infer that for two jobs I still have the same ratio. It's 2 plus 1 over alpha minus 1. Alright, so where is all this going? Right? So somehow we have to turn this into a general analysis. Right? Till this point it's been playing around with pictures. I can't do that in general. So this geometry has to somehow be converted into an algebraic definition. So let's try to do that. For that we will introduce a somewhat new idea that we call incremental analysis. The idea is that instead of trying to predict what opt is, or even what the final clairvoyant algorithm is doing, we will try to compare ourselves, the non-clairvoyant algorithm, with the clairvoyant algorithm on what we call the current instance. And what's the current instance? It's simply, for every job, I simply take the weight of the job that I have already processed. That's all I know in the non-clairvoyant setting. I don't know whether the job has more weight. So I define my current instance to be the processed weight of every job. And now on the current instance, there is some optimal clairvoyant algorithm. That's what I want to compare my non-clairvoyant algorithm to. Okay? So I want to compare the objectives of the non-clairvoyant and clairvoyant algorithm for this instance. Now what does this mean inductively? What's going for how do I maintain this property, this invariant, that the non-clairvoyant algorithm can be charged to clairvoyant for the current instance? So when I go from time t to t plus dt, my current instance changes. And since the current instance changes, my clairvoyant algorithm might completely change. From some curve it changes to a very different curve. Somehow I need to account for that. I need to be able to lower bound that objective, the change in the objective in the clairvoyant setting, and charge the additional objective that I incur in the non-clairvoyant setting to that increase in the clairvoyant case. Okay? So that's the general plan. So is the general plan okay? Okay, so let's see if this is able to solve our single job case first. So what happens when I change from an instance with weight W to an instance with weight W plus dW in the single job case? Well, basically what happens is the t equals 0 axis shifts to the left. Right? So I had weight W1. So I was starting my algorithm with power W1 and running on this curve. Now my new weight is W1 plus dW. So I'll start with W1 plus dW, and again I will follow the same curve. Remember, these curves are only defined by densities. It's not dependent on what the actual weights are. It's really just where you start that's defined by the actual weight. So that's the extra part that I'm getting on the left in the clairvoyant objective. What about the non-clairvoyant objective? Well, I'm getting exactly the same shape but on the right now because I've flipped it around. So now I can use my differential universality property to claim that the two rectangles there, the horizontal and the vertical segments, can in fact be bounded by just the vertical segment. That's exactly our differential universality property. Okay, so you can use differential universality to claim that in fact you are maintaining this invariant, that you can charge the non-clairvoyant solution to the clairvoyant solution. How about two jobs? Well, as from time 0 to R2, when the second job is released, it behaves exactly like a single job. It does nothing different. Now at R2, the second job is released, but nothing really happens in our analysis. Why? Because the non-clairvoyant algorithm continues to process the first job, and therefore the current instance has 0 weight for the second job. It hasn't even started processing, it doesn't know any weight. So really till the end of processing of the first job in this analysis, it's the single job scenario. Now once I've finished the first job, the second job starts getting processed, and then you get back to the setting that we had earlier. So basically this red curve in the clairvoyant algorithm gets shifted to the right, and this blue curve shows up in the middle. And the blue curve also shows up at the end there. And again, the differential integrality property basically exactly says that the B primes can be charged off to the B. This is what we did earlier as well. Okay? And this keeps happening, right? So the red curve keeps getting shifted and the blue curve keeps getting bigger. All right, so then what is the general algorithm? So this is the kind of analysis that we want to do. So what should be our general algorithm? Well, firstly, we want to process jobs in first in, first out order. So if you look at this picture, the red job is completely processed before I even touch the blue job. So clearly I'm processing in FIFO order in the non-clairvoyant algorithm. Okay, so I want to process jobs in FIFO order. And how do I set my instantaneous speed? So one way to think of setting the instantaneous speed is that I want both these algorithms to end at the same time. I don't want my the non-clairvoyant algorithm to lag behind, otherwise my analysis will go for a toss. So I simply set my speed in a way such that the non-clairvoyant algorithm doesn't lag behind. It finishes the same volume of job that the clairvoyant algorithm would have finished. Okay, and that gives me a unique speed, and that's how I set it, and therefore my analysis works. All right, so that takes care of the uniform density case. And that's pretty much what I want to talk about today. I'll tell a little bit about the arbitrary densities scenario. The difficulty with arbitrary densities is that it becomes messy and these figures don't work anymore. But I'll give you a little bit of an intuition as to what goes wrong and how we are able to fix it. So what goes wrong? Well,
but you know these densities up front.
You know these densities when it's released. Okay. So what goes wrong? Well, again, imagine there are two jobs, and the second job is at a much higher density than the first job. The blue job has a higher density than the red job. Okay? So when the blue job is released, it preempts the red job in the clairvoyant algorithm. It has the highest density first rule, and then once the blue job completes, you resume this red job. Now what options does the non-clairvoyant algorithm have? Well, one option is again try to mirror these two red and blue curves as it was doing earlier. Okay? What's wrong with this?
Density is large, right? So it should be the right way.
Right. So the blue guy has high density, and that guy is made to wait from R2 when it's released till the end of the first guy, the red guy. Okay? this clearly is suboptimal. I won't be able to charge this additional time that it's waiting. So that's bad. So it seems like I should really move the blue guy up front because it should be processed immediately on release. So this is what I should be doing, but there's a problem with this as well. At this point, I don't know enough about the red guy, about the red job, to be running my machine at high speed. So I'll end up running the blue job over a slow part of its curve, right? Because I haven't even seen the rest of the red job. So there's this two conflicting pulls. One requires, the analysis sort of requires me to go in, first out order. But as Mohit said, intuition suggests that really the highest density job should be processed earlier. So the way we resolve it, and this is not very unique, this is sort of the first thing you would think of, is to take the jobs and group them in densities, some kind of geometric bucketing. Now within the same bucket, you process jobs in FIFO order, first in, first out order. So these are jobs with roughly the same density. And across buckets, you use the highest density first rule. So if some job has a much higher density than the current job being processed, it will preempt the current job. But if the densities are close, it won't. So kind of the natural thing to do. However, this sort of messes up the entire analysis, and in fact it messes up the definition of instantaneous speed as well. So ideally, what should we want to do for setting instantaneous speed? Remember what were we doing earlier? We wanted our non-clairvoyant algorithm to finish as soon as the clairvoyant algorithm finishes. So we don't want the non-clairvoyant algorithm to lag behind. Now it turns out here we need a little more, because if we are exactly finishing at the same time as the clairvoyant algorithm, there are easy instances that you can construct where the adversary will force you to lag behind at some point. So in fact, non-clairvoyant needs to have an advantage over the clairvoyant algorithm in this case. Okay? So in particular, we want the completion time of the clairvoyant algorithm to be a constant times more than the current time, which is the completion time of the non-clairvoyant algorithm on the current instance, right? By definition, non-clairvoyant algorithm completes the current instance at current time, but clairvoyant we want it to be slower. So we want to run our machines at faster speed. Now one way of ensuring this is to say that I'll make sure that at the current time, if I simulated the clairvoyant algorithm, for every job it would have had a constant fraction of the job still left to process. Right? That would have ensured that the clairvoyant algorithm, let's say, will run for double the time. As it turns out, this is not an invariant we can maintain for every job, but we can sort of maintain this on average. So we can do some kind of an amortized analysis, and while this is not true for every job, we can show that if this is true for most jobs, or if this is true on average, even that is sufficient for the final ratio that we want. Okay? I don't want to go into details of this. Let me just state that the computative ratio you get for non-uniform densities is some constant where the dependence is not good on alpha. So remember, alpha was somewhere around 2 or 3, so that's not too bad, but from a technical perspective, we are not sure whether the dependence should be exponential or whether you can probably get better dependence. Okay, so let me end by mentioning a few open questions. The first one is not really an open question, but while the analysis for the uniform density case, as you saw, can be sort of pictorially represented, it's pretty easy, you can do it in a page or two. The proof for the non-uniform density case actually takes about 40 pages, 30 or 40 pages. Okay, so there's something we are not doing right there. There's probably a much simpler proof there, or maybe a different algorithm. Our dependence on alpha is not great in the non-uniform case. It's about 2 to the alpha, which might be improved, which might be possible to improve. And what's probably the most interesting thing here is, can we use this notion of incremental analysis somehow? So I think this is somewhat new in terms of the available techniques in online algorithms. So typically online algorithms don't work with changing instances. It's just one instance that they think about. So maybe this is useful elsewhere. Okay, thank you.
Questions?
So actually, can you go back to the this? Oh no, yeah, no, the next one, the result. So what? How does it depend on alpha?
What is the dependence on alpha? It's some exponent, I don't remember. 2 to the alpha?
I think the base is worse than 2.
Okay, but some is e to like some constant to the alpha.
Some constant to the
But it could be like 1 over. Sorry.
It's possible that you can get alpha squared or something.
Something. That is.
In fact, for the clairvoyant setting, well, even some more general scenarios, you can get polynomial alpha dependence.
For single machine, it's
Single machine is 2,
right?
but for more general, some more general settings, you have some polynomial.
Many machines are just this.
Do you know any lower bounds? So how
Not that I'm aware of, no. Lower bound suggesting that it's harder than clairvoyant. I think the clairvoyant case might have.
No, as alpha changes, you think should get harder, or like could it be constant independent of alpha?
Well, it's for the clairvoyant case, or for
Clairvoyant is 2, right? Independent of alpha.
yes,
But for the non-clairvoyant case, does alpha change?
yeah, we are not sure.
So in fact, the compare ratio for uniform density improves as alpha increases. Actually approach 2 if you have large alpha.
Well, the improvement is not significant. It goes from 3 to 2.
But
Yeah.
that's
But
still
3 is
Actually
uniform
decreasing
of
in
alpha.
alpha.
Yeah.
Yeah. For the
Yeah, the
uniform
2
density
plus 1
cases.
over alpha minus 1.
yeah, but it like for the non-clairvoyant setting as well.
Yeah,
right? Yes,
yeah.
for the
Yeah.
No, only for the
non-clairvoyant.
non-clairvoyant.
There is 2 anyway. Otherwise, huh?
The other one does not have a dependence on alpha.
Alpha. But here you're saying it's worse, but it's not like that's not
anyway, it
true.
goes from 3 to 2.
Yes.
But in this case, yeah, it's just.
For-
In this case, it's growing, yeah.
But you're saying it could be again a uniform constant.
Could be.
We don't have
It could be 3.
Yeah,
we don't
could
have
be
any
independent.
lower
for
bound.
example.
Alright, it's time then.